Hello everyone and welcome to a new video. And like I said in my previous video, which was like a few months ago, that I mostly will be using this channel as a way of documenting whatever I learn. And in the I also thought like instead of just making one video in like a span of 6 months or something like that, I would probably be a little more regular. I would probably be um, also sharing the knowledge that I attain as a part of documenting the stuff, as well as like helping others learn, right? Anyone who is doing the same thing. Um, so today we will be talking a little bit about Java, specifically JVM. I primarily use Java for creating backend APIs, and also I use Spring Boot. And I think a lot of people want to know about the internal workings of JVM. I wanted to know it, hence I read about it, I learned about it, and this is just me documenting that learning as well as passing on that information to you. Um, so let me just quickly pull up Obsidian, where I'm gonna just write stuff. Yeah, sorry, give me a second. I just need to map my tablet to this monitor. Yeah, does it work? Yeah. So we want to talk about JVM, right? So JVM stands for Java Virtual Machine, and what it does, how it does things, why was there a need of a Java virtual machine? We will talk about those things. Before we get started, you need to know about two things. That is a compiler. I hope I'm writing it correctly, and an interpreter. So, pardon me if the spellings are wrong, but yeah, a compiler and an interpreter. So, most of you may know what a compiler and an interpreter is, but I will just quickly gloss over what they are, and then we will enter JVM, right? So we know that machines primarily understand ones and zeros, right? And technically, even this is a misrepresentation because machines understand electrical signals, one being the presence of an electrical signal and zero being the absence of an electrical signal. So we created something called Boolean algebra so that we can represent that electrical signal in the form of ones and zeros. Um, and then basically so we can consider that ones and zeros, that is binary. We call it binary since there is only two values. Binary is the lowest level. Yeah, it is the lowest level that a machine can understand, or rather, you can think it is the best way a machine can understand, right? Lowest level for machine. Yeah, but we don't work with ones and zeros. If I just ask you to write a simple hello world program purely through ones and zeros, obviously no one will be able to do that. Unless you're insane, probably. But we write something which is a higher level language. We write in higher level languages. For example, we write in C, and we write in C++, and we write in Python, whatever is your flavor or your choice of language. So I have chosen Java. I use Java, and we will be talking about Java. So let's take Java for example. So we have system dot out dot println, and obviously there is some syntactical understanding that is required to still write this code, but this is still very similar to the English language. You can understand what a system is, you can understand the word out, println, and this is just a phrase, right? Any phrase you want to pass or print. So, and this is even more simplified after Java uh, 25. Now we just have io.println hello world. We don't even have to write the entire system.out syntax. Anyway, not the point here. The point is we write it in a way which is very similar to the human language of English, but a machine won't be able to understand this. And that is the very reason we introduce something called a compiler and an interpreter. So, to simplify, a compiler takes in your source code. For example, this is the compiler. It's also a program. So compilers and interpreters are programs. they take in your source code, like compiler takes in your source code as the input, and it spits out uh, the machine code. So this machine code can be something which is easily understood by your computer. And whenever you compile a file or whenever you compile a source code, it will create an executable program. Executable. Sorry about the dogs, by the way, if you can hear them. Yeah, it will create an executable program, um, which you can run to make your, like, whatever source code you wrote, that is equivalent to a computer program, right? So that executable file, not even program, executable program is the wrong term. So that executable file can be then run, and your program will work as expected. So this is compilation, where your source code is translated into machine code. And what is an interpreter? And why use an interpreter? Now, compilers are very hard to write. Compilers are not easy to write. And when JavaScript was being created by Brendan Eich, what he did was he created an interpreter for JavaScript, which would take your source code. So here's my interpreter. Oh, I butchered that spelling. Anyway, but yeah, it will take in my source code and it will read my source code line by line, one line at a time, right? And it will create a data structure which is called an abstract syntax tree. So let's not go into much about this, but if you're aware of a tree structure, data structure, so it will create based on yeah so it will create a structure which is similar to these, where each node of the tree represents some function, right? And how it performs that function, whether it does it in order, pre-order, post-order, that is determined by the interpreter's internal like code. That is not something you can handle. But let's say you want to write sum of some numbers, or let's say you just sum of a plus b, right? You write it in interpreted language, for example JavaScript. So you just say console.log a plus b, right? Yeah, you don't need the semicolon in JavaScript, but good practice. So your interpreter will create an abstract syntax tree where it might decide that it wants to first compute the value of a. So compute a, and then it wants to compute the value of b. So compute b, and then it wants to add a and b, and maybe this node is not needed, and finally it wants to print that. So it will create this syntax tree. And if I do a pre-order traversal, right, you will see that pre-order is going from the root, then left to right. So if I do a pre-order traversal, it will compute a. Compute a is the first thing, so it will get some value of a. It can be 5. Then it will compute b. 5 can be 7. It will add 5 and b, so it can be 5 plus 7 equal to 12, and then it will print the value. So this is my root. I compute it, then I go to the left node. This is my root again, so I compute this. Then I go to the left node. This is my root again, then I add it. Then I return, and then I go to the right node, and my right node just says print. So in the console, you will be able to see 12. Now this is generally how you traverse a tree and how it's done. But you're saying that it's just doing things step by step. So like, how is it able to do things step by step? I understand that the code is translated to a tree, but what is actually happening? What's actually happening is your interpreter will analyze your source code. Your interpreter will analyze your source code, and based on that, it will call a native code. By native code, it can be a code written in C++, which is a faster compiled language. It can be assembly, whatever suits well, whatever is the implementation of whatever, however your interpreter was implemented. So, for example, print 12, right? So there can be a corresponding assembly code, which is easier for your computer to understand. Uh, um, what it will do is your interpreter will call that assembly code. So it's like, if I have to give you an example, um, like what a compiler does and what an interpreter does. So a compiler is like a translator. You give them a passage of text, and what they will do is they will translate that entire passage. So your passage of text can be in Spanish. Your compiler will just go through the entire text and translate that to English. But what an interpreter is like, an interpreter itself cannot translate. It does not have the ability to translate. So what an interpreter will do, it will have like five different people, like five different Spanish speakers. For example, this is speaker 1, this is speaker 2, this is speaker 3, and this is speaker 4, and this is speaker 5. It will have five different people who speak Spanish, and it will look at your code and it will say, okay, this is a passage which can be well understood by speaker 1. So let me translate that passage by speaker 1. Or rather, let me make speaker 1 speak it, like understand it and speak it in English. Similarly, it can go to the next passage. It can think, okay, speaker 4 is probably the best option. Let them speak it in English. And after understanding the passage, let them speak it in English, right? So that's what, and it's not the best example, but I guess you have some idea of what's going on. So like an interpreter will check your code and it will say, okay, this code, this source code, it can be best executed by this assembly machine code. So let me run that assembly code. So that's basically how an interpreter works and how a compiler works. So why take so much time explaining compilers and interpreters, right? Because Java is both a compiled language and an interpreted language. Now the question is, why use both? Like, I understand if it's a compiled language, it's a faster language. If it's an interpreted language, it's a slower language. Because obviously compiled language, you translate once to machine code and you can run it and the execution time is fast. Whereas interpreted languages are like, even at the runtime, it's like creating that your abstract syntax tree, and then it's traversing that tree, and then it's calling the native block of machine code, right? So obviously interpreted languages are slower. So why would Java use both? Why can't it be just compiled for speed, or why can't it be just interpreted for simplicity? Because Java wanted to do, so that is something called, Java wanted to do write once. Okay, my bad. Yeah, Java wanted to do write once. Okay, I think my yeah, my hand is messing up the tablet. Write once, and okay, this is an issue, and run anywhere. So write once and run anywhere. That is, whenever you're using a compiled language, your compiled code is very dependent on your machine. So it can be it can be a combination of your hardware and your OS, or it can be just your OS or just your hardware, right? So whenever you compile the code, let's, for example, this is my Ubuntu machine, and I write a C++ code. I compile it using GCC, which is a C++ compiler, and whatever the executable that is being technically, yeah. So rather say, instead of saying executable, let's say whatever the machine code that is being spit out. Um, yeah, sorry. Yeah, whatever the machine code that is being spat out by the compiler, If we try to run it on my machine, that is Ubuntu, it will work completely fine. But let's say if we try to run it, if I take the same machine code, this same compiled machine code which was compiled on my Ubuntu machine using the GCC compiler, and if I send it to my friend who uses Windows, uh, and I ask them, okay, run this file on Windows, it won't work because the code was compiled using a GCC compiler, which is only compatible with my Ubuntu machine, and whatever the machine code that was being created, that is compatible with my Ubuntu machine. So if I ask them to run it on Windows or Mac or whatever OS they're using, it won't work. Okay, so that's one issue with compiled languages. We know the issue with interpreted languages, they're slower. So how did Java solve this? What what was the idea behind combining these two to achieve this write once and run anywhere logic? So what Java did was, whenever we have something called JVM, Java Virtual Machine, whenever you're installing JDK, it will be automatically installed with the JDK inside your system. So what Java has a compiler as well. So you will a lot of times you will see people write Java C main.java, where we are asking the Java compiler to compile our main.java file. So Java does not convert your code, your source code, to machine code. Rather, Java compiler converts your code to bytecode, and these bytecodes will have an extension of dot plus. Then this is fine. So we have an intermediary code, this bytecode, and then JVM will take this bytecode and JVM will execute it by interpreting that bytecode. Okay, but how does this solve that compile once, run everywhere, or anywhere rather? So this bytecode is independent of the type of JVM you're using. A lot of people, if you see on the internet, will say this bytecode is platform independent. Technically, I do not like saying that because this bytecode is not directly interacting with your OS or your hardware. So to say that the bytecode is independent of your platform is kind of wrong. Because let's say we had a for example we have an application which runs on any, like the executable runs on any platform, then you can say that the application is independent of the platform. But the bytecode is not running on any platform. The bytecode is being run by your JVM. So you can say that your bytecode is independent of any type of JVM that is being used. Then what is the bytecode? Okay, so bytecode is independent of any type of JVM. But the JVM itself is dependent on your platform. So if you go and try to download the JDK, you will see there's a download link for Windows, there's a download link for Linux, and there's a download link for Mac. So your JVM is dependent on these platforms, but your bytecode is not dependent on the type of JVM you're using. No matter the type of JVM you're using, if I send my friend the bytecode after I have compiled my Java file or Java project, and if they have a compatible JVM installed in their machine, they will be able to run it. And JVM will interpret this bytecode in the same way like I was talking about how an interpreter works. JVM interprets the bytecode and runs Java. And runs your program. So that's how Java works. That's why we call Java is an interpreted and compiled language, and hence Java is faster than interpreted languages because the bytecode that is being generated, that is easier to translate, like easier to be interpreted. It's not as slow as than translating a pure source code to calling functions. But it is not as fast as like a purely compiled language. Hence, you will see whenever you're comparing Java times, you will see it is faster than a language like Python. So Java is faster than, in terms of time, Java is faster than Python, but it's definitely slower than C. or C++, because C++ is a purely compiled language, and this is like not, I won't say purely interpreted. I think there's some hybrid of it right now as well, but this is a majorly interpreted language. Okay, so that's the majority of compiled versus interpreters, but we want to talk about JVM, and in the next video, since this has gone on for too long, I will talk about the internals of JVM. That is, we have something called a class loader, uh, followed by runtime data areas, followed by execution engine. And this is like the core concept of the JVM, how it takes your bytecode, uh, and then it basically, the execution engine is basically your interpreter. uh, not not just the interpreter, there are a few more things, but this is the part which is mainly responsible for interpreting your bytecode into like performing actions. Your class loader is the one which loads all the necessary dependencies. For example, you might be using like there are some like core Java classes, right? So java.util package, anything inside the java.util package is on the core Java classes. um, that is being loaded. Any dependency you have added, for example, I was talking about Spring Boot, right? So we generally add the Spring Boot starter dependency. So uh, if you have added that dependency, that will be loaded, and other custom stuff, whatever dependencies your project needs, it will be loaded by the class loader. Runtime data areas are mostly split into your stack, your heap, and your meta space, uh, where it's basically this stores metadata about your program, about your different classes, metadata about your project slash class files. Stack and heaps are just two different form of like memories. I will go deeper into them in the next video. Stack is mostly for method frames. For example, if whenever you're calling a method, it itself creates a stack frame inside your stack, and then it will have some like primitive variables and stuff like that, reference variables. Whereas heap will have like objects of classes and stuff like that. So yeah, we will get into this. If you watch this video, thank you for sticking by for so long. It was clearly not the best, but I guess it kind of helps to understand compilers and interpreters as well.